Hello everyone. So in this video, I will talk about the state representation that we started talking about it on Monday. Um, so here I have a circuit and I want to develop the state equations for this function. So actually I'm looking for the state representation of this function. As we mentioned before, the state representation looks like these two equations that we have here. So we have x dot equal to ax plus bz, and we have y, which is our output, equal to cx plus dz. Okay, so y is our output, as you can see here. X dot is the time derivative of the state variables. X is the state variable and z is the input. Again, the output and the input can be more than one. Okay, it doesn't have to be one. And the same thing is valid for the state variable. In the circuits that we have here, for example, the circuit that we have in this question, we have one capacitor and one inductor. So I have to first define my state variables. I know that state variables are the variables that I have access to their different derivative, the time derivative. What I mean is that since in the equations of the state representation, we have x dot over here, so we have to have access to the time derivative of that variable, that state variables. We know that in the circuits that we have inductor and capacitor, the variables that we have access to their differential equations, to their time derivatives, are the current passing through the inductor and the voltage across the capacitor. What I mean is that, so we know that the current passing through the capacitor is C dVc over dt. So the time derivative of the voltage across the capacitor, and then VL, which is the voltage across the inductor, is L dIL over dt. So the variables that we have access to their time derivative are Vc and IL. So I can say that my state variables are IL and Vc. So then I have access to their time derivative. X dot is dIL over dt and dVc over dt. So what I have to do here is to find the equation for dIL over dt and dVc over dt. If you look at the system of equations that we have for the state representation, the time derivative of the state variables are only depending on the state variables and the input. Nothing more than that. If I find the time derivative of one of my state variables, and then in that equation I have, let's say, an output, this means that I have to somehow manipulate that equation in order to get rid of that output, so I can have my differential equation in terms of the state variables and the input. And the same thing is valid for the output. You can see that the output depends on the input and the state variables and the input. Okay, so we'll work on this more when we start doing this problem. So for these kind of problems, whatever circuit analysis method that you're comfortable with, you can use. So you can use KVL, KCL, both of them. It only depends on what you're comfortable with or what approach you are using. So here, I will start with a KCL at node VO, where I wrote VO. So let's write a KCL at node VO. So at this node, I can see that I of C is entering the node while I of R and I of L are leaving the node. Oh, and another thing that we forgot to do here was to find the inputs and outputs. So in this class, for your exam, I will for sure define what are the inputs and what are the outputs, okay? But here, for example, this question, this problem in the book, it did not mention what are the inputs and what are the outputs, but we can clearly say that VO is our output and V1 and V2 are my inputs. Okay? All right. So let's go back to where we were. So we said that IC is equal to IR plus IL. Okay? What is IC equal to? I know that I of C is equal to C dVc over dt. C is 1 over 4. Then I have dVc over dt. That is equal to IR plus IL. So let's see if we are ready to put this equation in the state representation. dvc over dt, the time derivative of one of my state variables, is dependent on IR and IL. IL is my state variable, so we're good, but IR is not my state variable. It's neither my state variable nor my input. So I have to get rid of it. Let's see what is IR equal to. IR is the current passing through the resistor, and I can clearly say that it is equal to VO over 2, right? Now, if I substitute IR by VO over 2, we're still not done, because then I have the time derivative of VC in terms of the output and the state variable, while I need it to be in terms of the input and the state variable. For that reason, I can write a KVL in this node over here, in this mesh over here, sorry. Okay, so let's see what would that be. If I write the KVL, let's say this is mesh number 1. If I write the KVL there, I will have V1 is equal to VC plus VO. So from here, I can say that VO is V1 minus VC. Now, if I substitute this VO here, and then I substitute IR over here, then my equation will be ready to be placed in the system of equations. So that would be 1 over 4 dVc over dt. That is equal to IR. IR is VO over 2, while VO is equal to V1 minus VC over 2 plus IM. So then I'm going to just reorder this equation and multiply everything by 4 to get rid of the coefficient for dVc over dt. So I have dVc over dt will be equal to 2V1 minus 2VC plus 4IL. This will be one of the equations that will go in the state equation, right? We have the time derivative of the state variable Vc in terms of Vc and IL, which are my state variables, and also one of the inputs. So we're good here. Now, the other thing that I have to find here is an equation for dIL over dt, okay? Now, let's see how I can do that. So if you look at the voltage across the inductor, we know that the voltage across the inductor is LdIL over dt. But if I look at this part of the circuit, I see that VO minus V2, that is equal to VL, right? So from here, I can say that L dIL over dt, which is equal to VL, is equal to VO minus V2. So here I know that V2 is the input, so we're okay here, but VO is the output, so I have to get rid of that. So one thing that I will do, first I will substitute for L, which is 1, so dIL over dt. That is equal to, now VO, we already found it here, is equal to V1 minus VC minus V2, right? So we found an equation for dIL over dt, which is equal to V1 minus V2 minus Vc. So this is in terms of one of my state variables and both inputs. Okay, now I can take these two equations, so dIL over dt, and I have dVc over dt, that is equal to my matrix A multiplied by my state variables plus, so I know that my inputs are V1 and V2. So the matrix of my inputs are 2 by 1, right? So if I have a, actually, so the whole thing here should be 2 by 1, right? So if I only have a 2 by 2 matrix over here, that would be done. So both of A and B here are 2 by 2. Okay, so let's look at the equations. First, we have to look at the equation dIL over dt. I know that the coefficient of VC here is -1, while we don't have any IL here. And then for the inputs, it is 1 V1 and -1 V2, right? And then for my dVC over dt, which is this equation over here, we have 4IL, we have -2 VC, we have 2 V1 and 0 V2. Okay? So here you see that we found the first equation for the state representation, right? Now what I have to do is to write an equation for the output. So basically we did write this equation. Now we want to write this equation. Okay, let me write it down here. I know that y is equal to cx plus dz, right? So y is my output, and my output is just VO. So VO will be equal to, since my state variables are IL and VC, this will be a 1 by 2 matrix plus another 1 by 2 matrix multiplied by V1 and V2, right? Because when we are adding these two multiplications, we should get only a 1 by 1 matrix, which is equal to VO. All right. So up there, we found that VO was equal to V1 minus VC. So we already have the equation ready, because we know that it should be in terms of the state variable, which is, and the input, which is correct. Okay, so I'm going to only substitute, actually fill in this matrix format, this VO, with respect to the equation of VO. So VO is -1 VC, so we don't have any IL, we have -1 VC, we have 1 V1 and 0 V2. Okay, so what we did here was we found the differential equations for VC, and actually the differential equations for this circuit in order to write the state representation. You saw that first we define our state variables, then we try to find the time derivative of those variables, and then fill in this system of equations, which is the state representation. All right. So here I can say that this is my matrix A, this is my matrix B, matrix C, and matrix D. All right. So I hope you understood this problem. If you have any questions, please leave them in the comments down below, and I will see you in the next video. Thanks for watching.